Here. The question I think we left was that what is the difference between the resonant converter and the soft switching converter, right? If we are able to get on this 0 voltage switching in the soft switching converter, so why do we use the resonant converter? I think that's what the question was, right? So any idea why? What is the difference?
In my view, there is no resonant link between the AC. Means there are capacitor and inductor. This is making soft switching possibility, but there is no any resonant link in between.
No, that is there. So what is if let's say we do not have the resonant link or resonant circuit in between, right? It is good because we don't have to have external components, right? That is good thing. But now the question is basically if you can achieve the soft switching using the like not using any resonant component. So what is the advantage of resonant circuit then? So if you really look at we have the we have this one, right? So if we can achieve the 0 voltage switching here for this full bridge inverter without resonant circuit, right? And that's what we saw, right? We can achieve the soft switching or 0 voltage switching without the resonant circuit, right? So what is the difference between soft switching and resonant switching, right? Why then anyone will use resonant circuit? What is the advantage of using this resonant circuit? That's the question.
Current which is drawn from this full bridge inverter, it's has lot of harmonics, non-sinusoidal participate. Resonant it is.
Yes, but that is not a issue because what happened, our output is DC. So we are not looking like a DC has all the harmonics, right? So we are not looking for that one, right?
Will that harmonics not lead to some losses?
No, not significant. There may be some secondary fact, but not significant. What happened is that if you look at, we have this so there is always some leakage inductance here. There is always some junction capacitors of this diode. So what happened now is that when we are applying this voltage pulse like this here, so we see the voltage across this diode is not simply like this voltage pulse here, which is slightly, let's say this is VI, so this should be 2 VI, right, because of this center tap. So what happened here is that at this time, you see a lot of thinking because of this inductance and this capacitor. So because of that, your diode experiences a lot of voltage stress. So we have solved the problem on the inverter side, but we have not solved the problem on the rectification side. So at the rectification side, we have this high peak voltage, right, at the time of turn on, or turn off, sorry, at the time of turn off. And also, this steady state value, which is Vi, it keeps changing depending on the input voltage. So the voltage stress across the diode is not controlled. That is one issue. Other issue what happened is that if you look at depending on the frequency, so what we have small inductance, and then we have here the interturn and interwinding capacitance. So what happened is that depending on the turns ratio, right, what is the turns ratio, this capacitor could be quite significant. And again, depending on the current and power and other things. So what you see basically that you may see not a, let's say, this kind of current shape which we want to, like this. You might see some kind of strange looking current waveform. So the problem with this one is that, as we have established yesterday, that our ILA should be greater than I naught. I naught means when I naught was constant, so it should be the I naught peak. So now you have some of this peak current, so you have basically, you may lose the zero voltage switching, right? So this thing happen at higher frequencies, may not happen at the lower frequency. So what happened is that the resonant converters inherently give the ability to operate the circuit at much higher switching frequency. So let's say if you have a converter, if the soft switching on with this non-resonant converter, we may be able to switch at 200 kilohertz. But with the resonant circuit, we might be able to switch at 1 megahertz or 2 megahertz. So our frequency is always much higher than the switching frequency you can achieve with this soft switching circuit. So that is a big difference between the resonant and soft switching circuit. In case of resonant circuit, your practical switching frequency could be much higher than the switching frequency for the soft switching converter. Because the soft switching converters, we have a lot of parasitic components, they are not taken care. While in case of resonant circuit, is basically we have the smooth transitions of voltage and currents, and also some of these components become part of your resonant circuit. If you have a series parallel resonant circuit, then you can absorb the leakage inductance in the series and parallel capacitor in parallel, this intertwined capacitor in parallel to that. So it's if you really want to go to very high switching frequencies, then the resonant circuit enables you to go to those frequencies because you are able to absorb the parasitic components of the transformers, rectifiers, layouts, all those things.
So these components will be more prominent if we operate at a high frequency.
Yeah. And so since they are more prominent at those higher frequencies, they will create more problems. And but these components are absorbed in the resonant circuit, so the problem is not there. So right now, there is a lot of push for the converters to go in the range of 10 megahertz, right? That's happening because it's for a long time nothing has happened. Our switching frequency is still sitting about 250 kilohertz. That's what it has been there for the last 20 years. It hasn't changed. So now there is a lot of push now to go to the frequency much higher, right? Aim is to go to tens of megahertz, but we should be able to go to at least 7 megahertz. So I think like the shift in the real change in the frequency and all the thing, it takes time. It takes 20 years, 30 years. It doesn't happen in no time, right? So when I started in 1981, most of the switching frequencies were basically about to 10 kilohertz. 10 kilohertz of the, we say highest switching frequency is 10 kilohertz. Then it took 20 years to go to 200 kilohertz. So it will happen in, I think, in next maybe 5 years, 10 years, so we are switching in terms of megahertz, right? So resonant circuits basically enable you that high frequency operation. So that is the basic difference between resonant and the soft switching converter. So now, if we look at the So we discussed that if we are using, this is tune branch and this is tune, then we have the best of series resonant as well as the parallel resonant converter, and it is operating at constant frequency. The only drawback here is that we lose the 0 voltage switching for, let's say, this lag A. So for this side, we do the 0 voltage switching if we vary the pulse width quite a bit to take care of the input voltage variation. Otherwise, it has all the benefits. So now, what we can do is that we can use this auxiliary circuit where this is going to provide the source switching for the lag A. Because if you look at Now, what we can do is that this, here we have 0 volt switching, no problem. At this point, we can add the another component from LA, which will be so. As long as this current is high enough, we can have the voltage. And what happens is that in case of the non-resonant converter, so that is a pulsating current driving very fast, right? So it means you need very high current. But here current is going in a sinusoidal way, so the value of the current which you need for this thing is not that high. So these are some of the, let's say, hybrid converters where we're including the feature of soft switching converters and the resonant converters together. This we can apply in any circuit you want. So, if we this is the circuit we have seen, APWM converter. So one of the things here is that in order to maintain the zero voltage switching, the value of this Q has to be reasonably high. Reasonably high means maybe rather than 1, it is 2. And the reason is that in APWM, we have asymmetrical pulse, so we have a strong even harmonics. And because of that, we have the issues how do we get this 0 voltage switching if our duty cycle is very narrow. So in order to remove that effect, we have to have a few of this resonant circuit which is reasonable. But once we do that one, now the voltage stress across this inductor is twice. And what happened is that, because as I told you, these were for low power applications, 30 watts and so on. So the problem with that one is this inductor becomes quite critical. We're switching at high frequency, and now we have high voltage, high frequency, high voltage across the inductor, right? So you have a lot of losses there. Your core losses are quite high. So in order to reduce those losses, you have to operate at low flux density. And in order to operate at low flux density, you have to have bigger core. You need bigger core. So then what happens is that this inductor, the size of this inductor becomes quite dominant. So we can do same thing what we did in other circuit. So we can have this auxiliary circuit provides some assistance to get the 0 voltage switching. And now, if you look at basically the trade-off between these two inductors. So this inductor basically is much smaller than if you look at this inductor. So this inductor doesn't have high voltage stress. And it doesn't have to carry all the power. So it carries only the current basically which is required for the communication for software. Now, we want to operate these converters at very high frequency, and let's say we want to operate at 10 megahertz. So if you want to operate 10 megahertz, what is the period? How many seconds we have for the time period? For 10 megahertz we have how much?
0.1.
So we have 100 nanosecond. So we have only 100 nanosecond as your total cycle. And now, if you want to do pulse width modulation, PWM, then let's say you are going to 0.1% duty cycle. So now you have 10 nanosecond for that pulse. And you have all the feedback. You're sensing voltage, you're sensing currents, and so on. You have drivers basically to drive these MOSFETs, right? So what will you do in 10 nanoseconds? You'll have a lot of delays and other things. So what happens is that at high switching frequency, we cannot give the pulse width modulation. It becomes very difficult. What shall we do now? We have seen that if you want the best utilization of the circuit, right, then it should be switched close to the resonant frequency. Right? Close to the resonant frequency, the switch is slightly above the resonant frequency that is GVS, and then you get basically having the best utilization of all the components. So what happens is that at high frequency, what we can do is we can do something called pulse density modulation. So what is the pulse density modulation? Let us say we produce this is the current IS we are producing here, and this is VS, and we are operating this 50% duty cycle for the core switching. And we are very close to the resonant point. So what happens is that if we look at in this converter, we have, let's say, input capacitor and filter, we have output capacitor and filter, then we have all those things. They are frequency dependent components. So the higher the frequency we are going to have, the smaller the size we are going to have. But at high frequency we cannot do PWM. So what happens is that what we can do is that we can have this pulse density modulation, like rather than we have continuously on, we can have can have on off. You get a whole converter on for number of pulses and whole converter off for number of pulses. So when this converter is on, then it's always operating closer to the resonant frequency, right? So you have 0 voltage switching, it's closer to resonant frequency, have the best power transfer, right? And now there is basically you are not looking the small duration for the pulse width. So now you have a number of pulses, right? So you can modulate so that you don't have those time delay problems what you see in PWM. The only drawback of this scheme is that if you look at your output voltage, so output voltage will be, you are basically charging this output voltage like this, and here you discharge here and you charge here, and of course there is this ripple is between here. So now the on-off, the frequency of on-off determines the ripple in the output capacitor or input capacitor. So if we are switching at 10 megahertz and this on-off frequency is, let's say, 100 kilohertz, right? Nothing wrong. So what happened is that you have shrank all the components for 10 megahertz, but you have the input and output capacitors, right? Those are basically decided by 100 kilohertz or 500 kilohertz or 1 megahertz, whatever frequency you decide to use. And as I told you earlier, that in most of the applications, the size of those capacitors is not determined by the ripple, voltage ripple. It is determined by the dynamics of the load. So that is not a major, let's say, limitation. So this is what happening, that when we are going now, like we are pushing the frequencies for many megahertz. And what happens is that if you go about 10 megahertz, then you don't even need a core in the transformer. So they are the air core transformers.
Number of pulses are off during a certain time.
Yeah.
Is the pulse not being produced, or it's not being just gated? Or it's not being...
No, it's basically, if it is not gated here, pulse is not produced.
Then why the should be switching component to come off?
Oh, okay. Well, it won't be there. You're right.
This duty ratio is same as the point one we have wanted. We wanted. This on-off period.
This on-off period is basically, let's say you need 10%, right? So now this 10% basically, you can decide what frequency you want. You're basically, let's say you want this modulation at 100 kilohertz, right? So what happens is that now you look at it differently. What are how many cycles of this current you are going to have, and then you select those number of cycles what you want, right? So 10% means basically, let's say if you have 100 cycles for the full duty cycle, for 10% you have 10 cycles. So that's the only difference. So I think this is the only material I would like to cover a lot more, but now let us spend some time in case you have any questions, so we can have the discussion basically. Any question you have, we can discuss it now.
This concept of generating cycles, I think is being used in other applications also. This pulse density modulation.
That's true, right?
In normal meter also, I think this wherever high frequency is required, I think this is used.
Yeah, this pulse density modulation is basically it's a old concept, right? And it's not a new concept, right? But it has not been used in practical application, right? It has been explained, but it has not been applied, right? There are a lot of, it's not an easy thing to implement.
Low frequency is a similar kind of thing, it's known as integral cycle controls.
Yeah.
One of the
So now what happened is that in this one thing is basically that if you want to have the 0 voltage switching, so let's say you want to turn off at this point here, you will not turn off at this point. You will let this cycle complete, turn it off there, right? So you are implementing some of those techniques is not easy to implement. The other problem what happened is that all those things what we explain here is under the steady state condition. Everything is steady state, your currents are established, your voltage is established, and it's 0 voltage switching. But now what happening is that your circuit is going through the transients every time. So when it goes through transients, so during the transients, you may not have 0 voltage. As a matter of fact, you don't have 0 voltage switching. So how do you solve that problem? So let's say, for example, if you are switching this one on-off at 100 kilohertz, so you do have the losses corresponding to 100 kilohertz. So how do you make sure that you don't have the losses? Or if you want to reduce this capacitor further, just your control frequency 1 megahertz, then you have those switching losses at 1 megahertz. So now that is a problem. Like how do you basically achieve the 0 voltage switching during the transient condition? Those are some of the limitations, and we are working on this one. So I have one of the PhD students who is working on this one. How can we basically have this 0 voltage switching, or at least 0 current switching at the point? Otherwise, what happens? Yes, you won't have the losses corresponding to 10 megahertz, but you have the losses corresponding to 1 megahertz or 100 kilohertz, whatever this on-off frequency you have. So those are the problems which need to be solved.
Transients will not be at so high frequency at 1 gigahertz. It can be, because load changes not so fast.
If this is basically, this is their time. At what frequency you are doing it. Right? So anytime basically it's not a steady state. So what you see basically is you will see this. This is something like this.
How we sense the 0 voltage position, because there are many components, and we use the sensor for sensing the 0 voltage. So in the sensor there will be lots of losses. So how it is arithmetic process?
Yeah, so I think that is one of the challenges basically. How do you do it, right, at those frequencies, right? And one of the things is basically you don't want to use the sensors. You are moving away from the sensor. Right? So there is a lot of digital implementation. That's what it means. Right? And so it's basically that there is a lot of sensorless control. Okay, like you are not sensing the current, you are moving away from it.
What type of sensors we normally use in these soft switching applications?
Well, it's basically they're all, let's say, in the high frequency, they're all current transformers, right? And if they're on DC, they're all Hall effect. They're all Hall effects, and the tiny one comes in form semiconductor. But they are the most expensive components in the design.
Normally in our high power application, we use this Hall effect sensor. But I think there may be some smaller versions of.
Yeah, they're tiny version of Hall effect, which are coming. Yeah. You can use them, but they're very expensive.
They're having a better dynamics, I guess.
Well, yeah, they will have better dynamics. That's true. But the main problem is the cost. They're very expensive. They're about $2 each. So, yeah, so if you for sensors $8, which is a lot of money for a small product.
What would be the typical rating current of those sensors?
But we are using it because we are using them for a relatively small power. We are using them in few hundred watts application.
This one, current control.
To sense the current, yeah.
Sir, like output voltage and current is controlled by the pulses, switching pulses. So, what is the pulse control scheme here? Like this is the power circuit. How is the closed loop current PWM or?
They are mainly basically is a hysteric type of control, right? So there are thresholds, minimum and higher threshold, and that is determined by how much people you can tolerate there. So based on that one, we are on. The control is not a problem. The main problem is basically that how you take care of some of these losses there. That's the biggest challenge. And there are basically what happens is that some of the things when you digital control, you see right now we are making the assumption that we have this 50% duty cycle. Let's say it is 10 megahertz, it is 50% duty cycle, that's the assumption making, right? But what happens in the first few pulses, the transient, so you don't have that 50% duty cycle. You will have smaller duty cycle and you will even vary the frequency little bit at the time, right? So those are the two additional control variables you have, which is the pulse width and the frequency for the first few transient cycles. And they are helping to reduce those losses significantly. So it's difficult to get the 0 voltage switching and for the first pulse because current 0, you don't have that one. So, but you can get 0 current switching and then subsequently you can get 0.
For such a high application, high frequency application, when we use some control, current control voltage control, so we are using digital controllers. So exactly what type of digital controllers will be effective for
they are all FPGA based.
FPGA based.
Yeah, FPGA based. So you have FPGA based, and then once you have the your volume, then you convert them into IC. Okay, so I think Dr. Singh mentioned to me to discuss something about the current research, current trends, what's happening, right? So I'd like to spend little time on that one. So what happening is that okay. Pardon?
We can discuss there also. During the time.
Why don't we serve tea here? Are there?
Okay.
Yeah, they can serve tea here. Not everyone go. So you sit here. They will bring the tea here. Otherwise, no point. And then you get the custom toroid. So that has basically different material introduce this certain ear gap right inside the material. Yeah, that you can do. It is true that toroid is most efficient than the, let's say, your EA1 or kind of construction, right? But you don't have a material, let's say, beyond maybe 40-50 kilohertz. This is the used toroid. You would call fabric. So what happened? Is there any here or? Okay, so should I wait for other people or is that? So in terms of the, let's say what happened now is that particularly for this high frequency kind of area. So as you see that the most of the topologies they have been invented. It's a very little work left to invent a new topology. That's one thing. Second thing, what happened is that all the analog control is now being replaced by digital control. So once you have the digital control, you have additional flexibility. How do you implement, right? So what happening is that now this this combination of the circuit topology with the digital control is one of the let's say area basically to come up something new, right? So you have a circuit topology, you have the digital control, and now maybe some of this known circuit topology you can optimize them further through the digital control. So that is a lot of work basically happening there, like how do you optimize the post-circuit topology, particularly when going to high frequency, and then some of the things is basically how do you reduce these some of the external components, current sensors, voltage sensors, those kind of things, right? How do you minimize them? So that's what's happening. So it's all in the digital domain, right? That's one thing that is happening. Now there is work which is going on in the bidirectional converters. So what happening is that there is a lot of applications which are coming which require the bidirectional converters. Let's say we have more and more aircrafts going for more electric aircrafts. Eventually they want to go full electric aircraft, but in time. So what happens is on a typical, let's say, aircraft, so you have some energy storage, and that energy storage is done in fuel cells and the batteries at a low voltage, somewhere about 20 volts, right? Then you have a DC bus, which is about 160 volts, 200 volts. And then you have the AC bus, which is at 220 volts, right? So now what happened is that there are 3 different buses and they have different loads connected to them. So now you can optimize the storage energy by connecting these buses together. And the way you do it, you use this bidirectional converters, DC-DC converters, DC to AC inverters. So use bidirectional converter. So that is becoming a big challenge, right? How do you do that bidirectional converter? So let's say, for example, you're using a DC-DC converter using the, let's say, resonant circuit. So now, it's okay, I mean, you have the positive load, right? Positive current, and you can design the converter. But now your current is going both directions. It's changing from, it is going from full positive to all the way full negative to zero. So it's saying a lot of different kind of, let's say, scenario here. So you lose zero voltage switching. And if you lose zero voltage switching, right, it doesn't matter where you lose, you have disaster in your hands, right? The circuit is blown. That is another thing basically, how do you basically solve this zero voltage switching problem in the bidirectional converters when this power is changing from positive to negative? That is another thing that is happening. So there is one very popular converter topology is called the dual-active bridge. The dual-active bridge, basically what happens is that you have the, let's say, full bridge inverter, and your diode bridge is replaced by another full bridge circuit. The reason is because this full bridge circuit now can basically have the both sides, like your flow of the power, right? So one basically is an inverter, and another one acts as a synchronous rectifier, or vice versa, right? So there is this well-active bridge. So that is in the two bridges. You can vary the frequency, you can do PWM, you can do APWM. There's a lot of combinations, a lot of options in that. So that is another thing basically, like people are working on to optimize this gating patterns basically right along the whole range basically, that will give you the zero voltage switching while minimizing the conduction losses, right? So that is another area that is happening. And this bidirectional converters, they are used in, let's say, your electric vehicles. So in electric vehicles, basically, now you need a bidirectional converter because, let's say, you're charging your traction battery, right? Now, there in North America, that more than 90% of the cars, just they go from point A to point B, from home to work, and they park there, right? So now the amount of energy which is stored in the batteries, right, is so much. Let's say everyone is driving electric car, right? So the amount of stored energy will be that you can power the whole planet for 4 hours for anything. And now what happening is that you have the renewable energy sources, like the wind and solar. The problem with the wind and solar is that the intermittency of the source. You don't have sun, you have sun, you don't have wind, right? So there is a lot of, basically, this requires a lot of storage for the system to work properly, right? So now what happens is that within the smart grid, let's say, work, that your electric vehicles, right? Convertible electric vehicles are bidirectional. They can be used as a load or as a source, both of them. So there is a lot of work basically which is going on there. And then when you have this one, like you have to provide all the smart grid features, right? So you have to not only just rectify and provide the inverter, you have to do all this active power control, electric power control, all this all right through, right? frequency right through, right? All kind of things you have to take care of that part. So it's becoming very sophisticated thing. This converter is very sophisticated thing. So what you see basically, the basic circuit topologies are challenged because of the way they are operated, and then there are a lot of control techniques basically you have to implement or to basically provide all the features what you require. Let's say applications and everything. But the other one is basically energy storage, right? Energy storage. How do you store energy? Where do you store energy in the system? What do you do? Right? That's another big area which requires. But in essence, what happening is that there is a lot of emphasis on the lot of detailed mathematical work, right? To get a precise thing what is happening, come up with the precise models, come up with the precise, let's say, your getting patterns and other things, right? And then implement, and they all are implemented through digital control. And you cannot implement them in annual control. The annual control is hopeless. You will not do it. Right? But I think what will happen is that, in my opinion, most of the energy storage will happen at the point of use. So it will be more of the distributed kind of storage, right? You will see that more and more renewable energy system, you have PVs and backed up by these kind of storage. That's what we see, that will evolve. That will see next 10 years, that will take a major portion of the network. And I think all your big centralized sources, right? I think, I don't know when, but they will all replace, they will all gone. You will not, in 100 years you won't see the grid, it will be gone. Like your telephone, you see all the telephone lines you used to see, right? You don't see anymore. There's no need. So similarly, you will see that once you have the battery technology, right, develop further, solar technology already become quite mature, quite reliable, right? So you'll see most of them are the type of isolated energy system. Each home is very on 3 kilowatts and then the backup at 30 kilowatts. It will happen. It's a matter of time. The centralized will be there, but it will just wait for backup of where the last will come there. There won't be new investment.
There will be huge investment if it has to be everything. Like renovated or
so that's what I'm saying. So right now what happening is that if let's say more and more users use solar with the storage, they are off grid. Only grid. This will take time. It won't happen today, but it's starting to happen. There's a lot of off-grid activity. So you'll see the energy storage there. Yeah. You'll see the, but you won't see the large energy storage, because large energy storage is very expensive.
So tidal wave energy is loaded, plus wireless energy transfer.
Yeah, so wireless energy transfer basically is, I think, that wireless energy transfer will not help energy storage. Because you are producing energy and then transferring. Is a media of transmission and change, right? And the efficiency of wireless energy transfer is very, very low. So that will happen only for you are at the airport, right? So your phone will charge automatically. So it is done for very low power. That will happen, right? But for the major energy need, that will happen. There is another thing going on for the high voltage DC transmission for the offshore wind farm, right? So the other thing basically there, I think there's some good work will happen there. So right now there is lots and lots of emphasis on electric vehicles. Lot of research we have done.
What are the typical applications of this resonant converter?
So there are some applications where you cannot avoid resonance, right? That is basically induction between one, CFL is another one, then high voltage negative power supply another one. Then you simply cannot do, you have to live with resonance, right? But afterwards, you will see that these resonant converters for these, let's say, wireless energy transfer that require resonance converters. Your induction heater require resonance converters. Your what you call the lot of your space kind of applications have resonant converters. The high performance, wherever you need high performance, have the resonant converters. And now the resonant converters are being used in a lot of renewable energy systems, low power energy systems, because of the efficiency and make all that thing. So it's the you always have basically it's a it depends what is the need for the application. It will determine from there. But if you're going in higher and higher frequency, right, then you will see more and more resonant converters coming into the picture.
This equilibrium inverter that we're talking about, and used for the modular.
Yeah, so this APWM, I think we made this converter in 1992. This converter, and they were used for all the telecom applications. Where you have a, let's say, optoelectrical board, and this optoelectrical board has many different requirements for the voltage, right? So it's used as a quantity power supply. We are using the derivative of this thing now in the PV microinverters for PV, using converters, which is similar to this.
When we use these resonant converters in PV applications, so will it be able to be extract LPP applications and everything? Because it's very much JDS and other cannot be suited for voltage control or something.
Now why do we have it? This is a converter. This is a DC converter, right? So DC digital, you should be able to control any activity you want, and you should be able to get any output voltage you want. There is no limitation here. Actually, what happened, the reason we are using this one is because unlike a boost converter for MPPT, so this one is the much higher frequency, right? And it's a very high frequency basically, then you have very high MPPT efficiency. And the amount of capacitance you require at the input side is very small.
Generally, we use a transformer, boost converter, which is a non-isolated converter. But these are mostly isolated.
Yeah, so boost converter is basically, let's say if you have a microinverter, so you call this multi-volt. You want to go to 400 volts, you cannot use boost converter. You cannot boost 20 times, right? You cannot use boost converter. So you have to have a transformer, right? Once you have transformer, what kind of circuit you use, right? It all depends on that.
This can be used for high transformation ratio also.
Yeah, it can be. So right now we are using it from 20, input voltage 22 to 40 volts, and then we're producing output voltage from 360 to 440 volts.
You still know single stage.
So this is a DC-DC converter, and then it is followed by a DC-DC converter. And the reason is basically because the resonant converters allows us to get very high efficiency in a compact thing, and it's a different way we are using it. So what we are doing is that it is a, let's say for the microinverters, you have where most of the systems are single phase AC, right? So you have single phase AC, and then you have this solar panel, which is the DC, but we can extract the maximum power only one point, one operating point, right? So now, once you have the AC, and in between the electronics, you have this low frequency pulsating power, right? So how we deal with this pulsating power? So the pulsating power just goes and goes right through, goes across the panel. So when it goes across the panel, basically, there's no way you can track MPPT, right?
What is this pulsating power?
Because you are producing a single phase AC. So inside the converter, you have to produce the pulsating double the frequency, right? So now what we do is that people have done, they use the storage capacitor, electronic caps, they store that power pulsation and full MPPT and some people basically what they do is then they boost the voltage somewhere in between, and so that the amount of capacity you require is reduced because the voltage is half C square, right? So you need smaller amount of capacitance, right? But what we did is basically that we just use the two-stage converter, and we basically let this DC bus, high voltage DC bus, fluctuate whatever it happens, right? And we are controlling this DC input on the panel, and so we are tracking MPPT at 200 kilohertz. So rather than use 10,000 microfarad capacitor, we will use less than 10 microfarad. And then if you follow this converter, you can then step up your voltage, whatever you want, right? So because of there are so much of variation for the output load and the voltage and other things, so none of the converter basically is what here it won't give the software. So the regular converter you can get the software.
We are running short of time, so
yeah, okay. So thank you very much. Yeah, thanks.
Just a minute. We are going to have a gap right now. I'm going to distribute the question papers. It doesn't have any chorus for the name, so please write down the names here. Right? You have to answer in the same page, the front page and the back page. Right? After the exam, we'll be evaluating it later on, but we'll be giving the certificate of participation. So just don't go away. We will be, this is for half an hour, we'll be trying to finish it before 12. So we'll be assembling once again afterwards, certificate distribution. Okay. You have interacted a lot. I'm really thankful to my volunteers also, who have spared a lot of time. Thank you very much for being with us, and hopefully if you have any confusion, we'll be in touch in future also. Thank you very much. Now, I will request Professor Jack to distribute the certificates. I'm calling the names. I will say Awasthi. Can you clap? Amit Kumar. Akbar Ahmed. Malik Reddy. Bhavna.
Bhavna is there?
Janendra Kumar. Virendra Prasad. Umarlal Beniwal. Umarlal Beniwal.
And
Guru Manari.
Nadi Kumar Mishra. Chandrasekhar.
Chandrasekhar Nilamati.
Nitin Ramesh.
Dr. Paulson Samuel.
Pushpendra Yadav.
Pushpendra Yadav.
Rajat Kumar.
Rajesh Gupta. Mr.
Rajiv Kumar.
Rajiv Kumar Maurya. Dr. Rishabh Shukla.
Sandeep Kumar. Sanjay Shajilat Sandeep Banerjee. Sandeep Banerjee. Sir Saurabh Srivastava. Umesh Kumar Soni. Vibhor Mittal. Vibhor
I will request Dr. Mira Pansal. Thank you very much and
convey word of thanks to Professor Jain. And so it's been a very wonderful course and very close to the topics which we used to teach in our UG and PG students. And I first of all actually envisaged this particular topic and arranged this course in our department and invited our esteemed Professor B.K. Jain from Canada, and it's been a very prestigious moment actually, and we are actually blessed by presence of Professor B.K. Jain. He spared his valuable time. His schedules are so hectic, but still he is able to find out time for us and spared his valuable knowledge with us. And it will be really very useful if we use his techniques and the methods he presented to us. I am also thankful to our head of the department, electrical engineering, who assisted us in all the steps to make this program successful. I am thankful to our honorable director, Professor Rajiv Tripathi, who made this all so easy and helped in all the aspects of administrative and technical supports to make this program successful. Now I finally thank volunteers who spared day and night to make this program so successful and arranged in such a nice manner. And thanks to all the participants who came from faraway places and attended this course. Thank you very much.
Thank you.